Look at this limit. As x slides towards 0, the top, sine of x, heads to 0, and the bottom, x, heads to 0 too. So you get 0 over 0. And that is not an answer. It's a question. 0 over 0 could be anything. Here's the proof. Every one of these three fractions becomes 0 over 0 when x goes to 0. Yet the first settles at 1, the second collapses to 0, and the third blows up to infinity. Same empty form, three different destinies. What decides the winner is not where the two functions are. It's how fast each one is moving. And speed is exactly what a derivative measures. So here is L'Hopital's rule. It steps in for exactly one situation. You have a limit of a fraction, and substituting gives you 0 over 0 or infinity over infinity. Then you're allowed to do something that looks almost too good. Replace the top with its derivative, replace the bottom with its derivative, and take the limit of that new fraction instead. One warning up front, and it's the one people trip on. You differentiate the top and the bottom separately. This is not the quotient rule. There is no messy g squared anywhere. Just f prime over g prime. This works as x approaches any point A. And it works just as well as x runs off to infinity, as long as the form was infinity over infinity. Now let me show you why this is even true. And it's genuinely beautiful. Picture two curves, f and g, that both pass through 0 at the same point A. Zoom in really close to A, and something magical happens. Every smooth curve, up close, looks exactly like a straight line. It's tangent. So near AF is practically f prime of A times x minus A, and G is G prime of A times x minus A. Now form the ratio. On top, f prime of A times x minus A. On the bottom, g prime of A times x minus A. And watch, the x minus A on top and the x minus A on the bottom cancel clean away. What's left is simply f prime of A over g prime of A. That's the whole rule, sitting right there in the geometry. Let's cash this in on the limit we started with. Sine of x over x as x goes to 0. First, always check the form. Sine of 0 is 0 over 0. That's 0 over 0. So we're cleared to go. Differentiate the top. The derivative of sine is cosine. Differentiate the bottom. The derivative of x is 1. So the limit becomes cosine of x over 1. Now just substitute. Cosine of 0 is 1 over 1. The limit is exactly 1. That famous result you may have memorized falls out in a single line. One more quick one, same rhythm. E to the x minus 1 over x. Substitute 0. E to the 0 is 1, minus 1 is 0, over 0. Indeterminate again. The derivative of e to the x is just e to the x. The derivative of x is 1. So we get e to the x over 1, and at 0 that's 1. Painless. Sometimes one pass isn't enough. Take 1 minus cosine x over x squared as x goes to 0. Check the form. 1 minus cosine 0 is 0 over 0. Good. Differentiate the top. The derivative of 1 minus cosine is sine. Differentiate the bottom. The derivative of x squared is 2x. But look at what we've got. Sine of x over 2x. Substitute 0, and it's 0 over 0 all over again. So we simply apply the rule a second time. Second pass. The derivative of sine is cosine. The derivative of 2x is 2. So now it's cosine x over 2, and that's finally determinate. Substitute the last time. Cosine of 0 is 1 over 2. The answer is 1/2. To clean applications, and the fog lifts. L'Hopital handles infinity over infinity just as gracefully. Here's a classic. X over e to the x as x runs off to infinity. Both top and bottom raise to infinity. So the form is infinity over infinity. Differentiate. The top, x, becomes 1. The bottom, e to the x, stays e to the x. Now it's 1 over e to the x. and as x grows, that crashes to 0. And the picture tells the whole story. Watch the green line, x, climb steadily. Now watch e to the x in rows. It doesn't just win, it obliterates. The exponential flow leaves any straight line in the dust. So the fraction, small on top and gigantic on the bottom, is squeezed to 0. The lesson underneath: exponentials beat polynomials, and polynomials beat logarithms every single time. Now, the single most important habit and a cautionary tale. The rule only works for 0 over 0 or infinity over infinity. Break that, and it lies to you. Take 1 over x. As x goes to 0, substitute. This is 1 over 0. That is not indeterminate, it just blows up. The true limit is plus or minus infinity, depending on the side you approach from. But suppose you didn't check and applied the rule anyway. Derivative of 1 is 0. Derivative of x is 1. So you'd get 0 over 1, which is 0, a flatly wrong answer. That mistake is the whole reason we check the form first. L'Hopital only speaks the language of fractions. But plenty of indeterminate limits arrive in other disguises. 0 times infinity, infinity, minus infinity, or powers like 1 to the infinity. The move is always the same. Reshape it into a fraction first. Let's do 1 cleanly. X times natural log x, as x approaches 0 from the positive side. As x shrinks, x goes to 0, but log x dives to minus infinity. So it's the tug of war 0 times infinity. The trick: park the log on top and push x underneath as 1 over x. Now it's log x over 1 over x, which is minus infinity over infinity. A legal form at last. Differentiate top and bottom. The derivative of log x is 1 over x. The derivative of 1 over x is minus 1 over x squared. Now simplify. 1 over x divided by minus 1 over x squared is just minus x. And as x goes to 0, that goes to 0. So the original limit is 0. And when the trouble is up in an exponent, a form like 1 to the infinity or 0 to the 0, the key is a logarithm. Take x to the x as x approaches 0 from above. That's the shape 0 to the 0. Call it y. And take the log of both sides. Log y is x times log x, and we just showed that goes to 0. So log y goes to 0, which means y itself goes to e to the 0. That is 1. The logarithm turned an impossible power into the fraction we already knew how to beat. Your turn. Evaluate e to the x. Minus 1, minus x, all over x squared, as x goes to 0. Pause the video right now and work it through. You'll likely need the rule twice. I'll wait. Here's the walkthrough. Substitute 0. E to the 0 is 1, minus 0, all 0, over 0. Cleared. Differentiate. The top becomes e to the x minus 1, the bottom becomes to x, and that's still 0 over 0. So go again. The derivative of e to the x minus 1 is e to the x. The derivative of 2x is 2. That gives e to the x over 2. And at 0, it's 1 half. If you landed on 1 half, beautifully done. Trap 1. The big one. Only 0 over 0 or infinity over infinity qualify. On any other form, the rule gives a wrong answer. Check before you differentiate. Trap 2. Differentiate the top and the bottom on their own. It is not the quotient rule. No g squared, no cross terms. Trap 3. After every application, check the form again before reapplying. Skip that, and you either stop too early or grind on forever. And trap 4. Sometimes it loops back to where you started, like root x squared plus 1 over x. When that happens, L'Hopital is a dead end. Step out and use another method. Let's lock it in. When a limit gives 0 over 0 or infinity over infinity, replace top and bottom with their derivatives and take the limit of that. Differentiate the numerator and the denominator separately. Never the quotient rule. Recheck the form after each pass. Apply again if you must, and reshape any other indeterminate form into a fraction first. Master those 3 lines, and these limits stop being scary. They become almost easy.